Yeah, so I hope it's visible.
Yeah, yes, please.
Even now.
Yeah, yeah, it's visible.
Yeah.
Team members, you may switch on your video if you want to, if the bandwidth permits, but if there are issues, then it's not mandatory. All right, so with this, we'll begin with the presentation session for the second half. Team 8, you can start your presentation.
So yeah, good afternoon all the judges, and we are teammate, and we are here to present uh, the solution to the BOSCH model extraction attack for video classification. Here we discuss our approach and the results of it. So this is the agenda for the presentation. I'll be covering the problem statement and the black box approach, and my colleague Harsh will be covering the gray box approach and the scope for improvement. Okay, so the problem statement asks us to develop an efficient strategy to extract video-based models in the black box and gray box setting for the following models and the following datasets. Our team working on this challenge believes that the true method of knowledge is experiment, and through this PPT, we intend to sequentially showcase our approach and thought process that went into solving this problem statement. So let's start with the black box approach. So we'll be covering the extraction strategies, models used, and then we'll be moving on towards the result. So we begin with random normal sampling, where each pixel in the video is randomly sampled and then is fed into the victim model as well as the clone model. The victim model's output logics and the clone model output logics together form the loss, which is the KL divergence loss. To train the clone model, we backpropagate through via autograph and then update the weights. We observed that we noted that the randomly sampling was unable to capture rich structure of a probable input space. Nevertheless, this gave us a framework to build upon. Then we move on towards another approach, which was training generator and clone together. Here we add another component to our existing framework, which is the generator. This helps us to generate meaningful videos. We hope that it helps us to generate meaningful videos. And the generator is trainable. So the loss function is calculated as shown here, which is a cross entropy. And while backpropagating to the clone model, it can be simply done by autograph, whereas we cannot backpropagate to the victim model as simple as that. So we apply a zeroth order gradient estimation technique, which is in the black box. The clone model here is still being trained via backpropagating to with the loss function LC. Okay, so this approach was also presented in two of the previous papers, which is model scaling attack using zeroth order gradient estimation and data-free model extraction. So we have built upon these approaches and included these for videos. These were earlier performed on image classification. So the generator used previously is based on the DVD GAN generator architecture, and the generator weights are updated using zeroth order gradient estimation. We observed that there was a severe mode collapse in the previous technique, and hence in an attempt to solve this, we trained the conditional generator separately before introducing it into the framework. We hope that this provides some prior knowledge before the generator impacts the clone training. So this was the generator training step, where it is a conditional generator and it is conditioned on labels. And then this train generator is then included into the previous framework and then is trained along with the clone model, similarly as I presented in method 2. Okay, please note that the generator is still being trained along with it. So this was the third approach. And the fourth and this is not actually an approach, this is just an experiment which was performed to validate a framework. We took images and then transformed them and stacked them to produce a video dimension or a temporal dimension, and then pass them through the model and train the clone model. So the results were something like this. We performed a fine transformation to singular images and then tried to make a temporal dimension out of it. Moving on to the generator model, the generator used here was a DVD GAN architecture, since it gives us state-of-the-art results in video generation and also satisfies the criterion of it being a conditional generator. Please note that it was an untrained generator and no pre-trained weights were used here. Clone models, same case, no pre-trained weights were used, untrained completely. We use a ResNet 3D, which was within our computational limits and also had a readily available code. We also move on to ResNet 2 plus 1D a bit, since it was among the top 20 in video classification related tasks. So this was about the models, the components of our framework. Now let's move on to the results. So these results are experimental results with video swing transformer as a feature. Normal sampling gave us expected results just above crossing random guessing level, which was 1.26% on top 5. Including the generator into the framework gave us 2.69% a boost, but not that much. Training a conditional generator independently also gave us a boost, which led to a final accuracy score of 4.85% top 5. And then the final experiment which we conducted, stacking affine transformed images, didn't lead us to good results, but we didn't focus on that a lot. We weren't allowed to use it. Okay, so the best experiment from the black box approach was then transferred to the MovieNet. Black box 20 approach was then transformed to the MovieNet approach, hence developing a common strategy as asked by the problem statement. On this, we got a top 5 accuracy of 4.85% on video spin and 4.13 on MovieNet P2 data, both with the clone model as R2 plus 1. That was it for black box, and the gray box approach will be continued by my colleague Ashima.
Hello. That to make a better model. I'll explain in the same slide. I'll explain the same format. I'll go with extraction strategies first, then models used, and then the results will follow. So the first approach that we followed quite obviously was to augment the dataset and apply rotation, horizontal flips maybe to the videos, and then pass them through victim and clone. The setup is very similar to what we have seen in black box. We take the input, augment it, and pass it through both teacher and clone, and then backpropagate the loss through clone only. Augmentations are done to make the model more robust and so that it generalizes better. We fiddled with the losses a bit. We tried MSC, etc., but we settled for KR divergence because we have a probability distribution to match, and KR divergence works best there. Then because we needed more data, we concatenated UCF and HMDB. Both of them are video-based dataset, but note that we didn't use the true labels from there. We just used the videos, passed them through augmentation, fed them to our network, and backpropagated the loss. We use the dataset so that we can have more data. More data is always better. The loss remains same, KL divergence, but we switched the clone model here. We switched to R2 plus 1D. And by this time, we also tried to fiddle with the learning rate. And by tweaking it, we found that a low learning rate around 0.003 works best. So we settled for that. Here are some snapshots from those datasets. On the left is UCF, and on the right is HMD. Then we moved. Then we tried an approach called adversarial grafting. This was we got to know this approach from a 2018 paper called Prada. So what this approach does basically is it takes an input X and it randomly perturbates it, like randomly perturbation, and it uses a method called FGSM, which is fast gradient sign method. What it essentially is when given an input X, it transforms it into an adversarial example by using the sign of the gradient. So it takes in the next slide I have a photo of that. So we use adversarial grafting and random perturbation here. The rest of the pipeline remains same. We have the input, augment it, generate some synthetic samples, pass it through the model, and back propagate the log. To explain more about Prada, so here Prada was actually for images in the original paper, but we extended it for videos in our approach. You can see in the image below that given the input X, it just perturbates it using FGSM to get an adversarial example to make our model more robust. Finally we tried to incorporate knowledge distillation techniques into our model. We switched from single loss to two losses. So we divided our input into two parts: UCF and SMDB in one, and kinetics in the other. We passed them. So for UCF and SMDB, we took the normal KL divergence loss that we have been taking for the past three experiments. We took the KL divergence between SMDB UCF on our victim and clone, and then we trained on the true labels of kinetics on true labels of kinetics, and we use a cross entropy loss there. We did that because like a forward KL divergence encourages similarity between the labels, and then cross entropy loss just makes the model more confident that it is actually predicting the right labels. Then both of these losses are combined and back propagated. We also gave more weight to the cross entropy loss. You can see that in the lambda is less than 1, providing more weight to the true labels. This is also the final model we use for reporting our results, as it worked best. Right. So for the clone models, we started with C3D. It was a purely convolution-based network quite long ago, and it was pre-trained on Sports 1 million. Then we went to ResNet 2+1D. This was fairly advanced. Trained on IG65, it does quite good in video classification related tasks. So these are the results that we obtained keeping Swinty as our teacher. So starting off with C3D, we had an accuracy of 27.5. Changing it to R2+1D gave us a huge boost, courtesy to the complex architecture of R2+1D. We jumped to 42.5. We increased the data set. Better, big data always better, 51.8. Then we tried Prada a bit. Prada was sounding very good theoretically, but like we couldn't get the results from there. We saturated around 35% in that. Combining knowledge distillation techniques and using a cross entropy loss on the true labels boosted us to 55%, which is our final accuracy. So finally, these results we were able to get these results on the gray box on video swing transformer using this last setup. We were able to get 54.8%, and then we transformed the same architecture to the MovieNet, and keeping R2+1D as the clone model, we were able to get 50.4% accuracy. Following this, we figured out some scope of improvement that we have. So for black box, increasing the number of queries multifold would help us, and selecting a good prior data distribution is important. And also we experience very frequent mode collapses with the generator. That's because our generator was not very robust. It was predicting the same class. So we think that we can improve on this. We can use maybe a different architecture or a different loss function, like in WGANs, where the discriminator is where the discriminator doesn't predict that the class is real or fake. It acts as a critique and ranks the realness or fakeness of the video. Then for the gray box, more extended training duration and faster hardware would help, because we were seeing that in our final model, the accuracy was on an upward slope. So given more time, we could have improved the accuracy. We could use generator to create synthetic data, and we can use a transformer model as a clone, because these days transformers are being used. So a transformer could have been a better student. Then we could have used adversarial crafting in a better way. As mentioned, we used Prada from this approach, but Prada was for images. We transformed it to videos, but we think we need to fix some more nooks and crooks to make it work and give us good results. That was for the scope of improvement, and we use these papers as references. This is not an exhaustive list, but this is what we found best. And yeah, that was it from our side. Thank you for your time.
Thank you, team. It was nice presentation. We really like the way that you have done an approach in a systematic way, and you're truly stick to what William Black has said. So kudos for that. First question is that in a gray box, you have used only 0.4 million queries, while in your black box, you have used the 1 million queries. What was the reason behind these two distinct numbers?
Yes, I'll answer. So in black box, you don't have any prior data distribution, and like generating a whole video takes a lot of queries. So for the generator we use, to even stabilize it, we needed like half the number of queries, right? So to stabilize the generator and get it to predicting some videos which are actual videos, like on which Swinty can actually work, is a very difficult task. So number of queries increased from there.
Okay. Yeah, and just to add to that, we had, while solving this problem, we had given more time towards the black box approach. So we had trained it for around, 5 to 6 days. We had the total training time, and it was put on training for a long time. That is why you will observe that the number of queries which we had in the black box were much higher compared to the gray box setting.
Understood. Thanks for that clarification. Am I right in saying that if I give you a more time with respect to the gray box, and if you take it to the 1 million, your accuracy will shoot up? And if yes, what is your estimate that it will shoot up? By how much?
Absolutely. Even after submitting, like when we had our first submission, we were at, I don't recall what our accuracy was, but I think 42. There was around 42. So around 10% of an increase we got from our, from the first submission to the second submission. And even now, we just left that on training, and we were seeing that we were seeing some increase towards, we were almost touching 65% accuracy towards the end. So if we leave it on training, we are confident that about 70% maybe we can reach, but I can't give any firm comments on that, but we'll definitely see a increase in our accuracy.
Understood. Thanks, Apurva, for that clarification. The follow-up question to that is that you have seen this accuracy increase after submission. Was it because of the new data, or was it because of allowing it to train for a longer time?
I think it was because we allowed it to train for a longer time, but we'll need to conduct some ablations to get to the root cause of that.
Okay. Fair. Questions? Please.
Yeah, first of all, well done. The systematic approach is really good. I had a couple of questions starting from black box already. I see that the back propagation for the generator goes through the victim model. Can you help me understand what's happening there?
Exactly. Let me help you there. So the victim model is in a black box, and hence we all know that we cannot backpropagate through it.
Can you go back to the slide?
Could you go back to the slide, please?
Exactly.
Yes. Here, right? Am I right?
Yeah, for example.
Yeah.
Or
So
in fact,
the
even
victim model is
The first one, right?
Slide.
Yes, random mouse. Correct.
Even before this, did you have anything? No.
No, we don't have anything here.
Okay. Then you're right. You're right. The second one. Correct.
Yeah. So the victim model is a black box, and we all know that we cannot backpropagate to it. Hence, we use zeroth order gradient estimation techniques, which involves like adding random perturbations to the initial input and then calculating the difference. I mean to say the gradient is approximated by d of f by d of x. The d of x is changed, and then we get to the final output model prediction.
Okay.
All right. And another question, why do you think the loss metrics that we have here for the generator and for the clone model are different? Why in the same architecture?
In a black box on option 2, please.
Yes.
In your black box setting on the option 2 or the experiment 2 which you have conducted, if you stay there on that particular slide.
Yeah, exactly.
Yes, exactly. Yeah.
How do you think this benefits cross entropy and KL divergence? Why do you think there are two matrices here? Can you explain on that? The design choice.
Yeah, we did experiment with the KL divergence, and this yielded better results for us. Maybe we have to go a theoretically bit deeper into the.
Okay, so the design decision was through experiments, and you found that.
Yes.
All right.
Now the lambda question, right?
Yeah. There was this elastic
gray box.
You had a hybrid L1, L2 loss where you had combination of cross entropy and KL divergence. Was lambda a hyperparameter or did you fix it?
Yeah, it was a it's supposed to be a hyperparameter, but we fixed it. Like we couldn't tweak it a bit. We tried, I guess 1/10 and 1/12, right? Yeah, 1/10 and 1/12, 1/10 work best.
Okay.
So essentially, you are telling in that case is that the KL divergence of a 10%, let's say,
Yes.
something like
The
that.
KL divergence has a 10% say, and the cross entropy
That is a 1, so 1:10.
Yeah.
So essentially 91% is on the cross entropy and 10% the KL divergence. But a KL divergence is actually on the victim model and the clone model, but your cross entropy, you are looking at the true and all of these things. So why this was a difference here?
So we believe that like KL divergence helps us to match the probability, and then finally the cross entropy just makes the model more confident that what it is projecting is actual labels. Also to note, KL divergence, when we took KL divergence, that was on UCF and HMDB, and the true labels were only used for Kinetics 500. So that
Understood. But what gives you a confidence that the KL divergence will really work? Because KL divergence is the distribution to be closed kind of a thing. But the data set which you have used is kind of a highly open-ended data set. So what is the confidence that give you that the KL divergence will really work in this case?
Mostly previous experiments, till experiment 3 were using KL divergence, and it boosted up to 42%, around 45%. So KL divergence was indeed working. We just like reduced its influence over that because we believe that we need to take into account the true labels also. Like we need to make the models more confident. We saw in the results that it was like not fairly confident on some queries. So we thought that come on, let's bring on the true labels and make it more confident. So we went on cross entropy. Yeah.
Do you think one more LC3 will be helpful?
Well, nothing can be said about that. But we don't see like on what quantities will apply the third loss. Is like we've already taken into account distribution, the cross entropy is there, the labels are at play. Yeah.
The thing which you have not considered here is the temporal variation kind of a thing. All of this particular losses works really well when you have the image related things, but for the temporal, these are not the good enough losses.
Yeah, that is a food for thought, and like to think on that. Yeah.
Okay, good discussion.
One last question. If it might have been useful for LC2 if you had visualized the posteriori distribution.
Yes.
Because you never know if a particular class has fired or not. Have you done that? Have you visualized the posteriori distribution?
No.
Maybe it's useful to look at that because there are, let's say, 400, 600 classes, and we do not have we cannot surely say that all the classes have been fired with 1 million, even 1 million.
I get that.
That's something you might want to.
And that is the reason that your KL divergence only works effectively for a very low amount. And that's why the closed distribution is not really mapped there. So good for thought, but really good approach.
Thank you.
Said all of this very good approach.
Thank you.
Thanks. So
I think that's all from our side. So thank you and all the best. Thanks for your time.
Thank you. Thank you for listening. Thank you.
Thank you, teammate, for presenting. You can now lower your hands and stop presenting the screen. Team 3 members, you could raise your hands now. So is it just going to be the two of you, Prajwal and Vivek?
Yes.
All right. So you can share your screen, and when you're ready, you can let us know.
Good afternoon, everyone. We are from Team 3, and today we will present our approach is overfitting all you need for the BOSCH model extraction competition. So first of all, let's understand the situation. For a model, we have 5 major things: model architecture, weights, logics, class labels, and the interclass information. So by model architecture, we mean the type of model, the number of layers, the type of layers, and what is the overall architecture that we have. And then we have weights for the model. For these weights go into the model, and then we get then these get multiplied, and we get some computation, and then we get the output. Next, we have model logits. By model logits, we mean that there is a probability that this sample belongs to this class. And then if you take the maximum, the sample, the logit with the maximum probability, then we have the class label. And these logits also tell us about the interclass correlation. Next, I will illustrate on the interclass correlation. But first of all, let's go into the black box setting. For the black box setting, we don't have any of these. We don't know any of these. So this is like difficult and a practical problem that we need to solve to have some real life impact. Next, let us go into logits. For in logits, like most of the times, logits are not orthogonal. For two different class samples, for example, let's say we train a classifier for classifying between dog, cat, and a cheetah. Then if I give a cat image, then there will be a correlation between cat and cheetah. If I give 100 samples, then you will see that there is a correlation between cat and cheetah. And this is something that is very crucial in this more attack setting, because this tell about like which class is correlated with other class, and this gives information to get a better idea of the model and to get a better idea of the classification, the type of classification, and how it is happening inside the model. Next, we have another major thing that we don't know the class labels. For example, if I give a sample of like the same classifier, cat, dog, and cheetah, then if I show a sample, then it will give only an index 0, 1, or 2, not the label, so that we cannot scrap any data from the internet so that we can use it for training. So we need to devise our novel approach somehow to make our own data and to extract some images or videos out of it and then train our clone model. So next, my friend will tell you about the literature survey and the approach.
So the state-of-the-art model which we explored, like knockoff nets and data free, they relied on some form of data, and they were both based on logits, but we were only given the top class labels. Also, the approaches like copycat CNN, which relies on which works on labels also, but it relies on in distribution or out distribution data to train itself. In our case, we cannot use any data other than synthetic data, which should be generated by the approach itself. Now let us go to the approach.
All right. So as my teammates have explained, we have basically two problems to tackle. One is to generate the data of a class, and second is to capture the correlations between the two classes. So the novelty of our solution arises from the fact that we are isolating these two tasks between two different networks, which you can say this technique has been inspired by similar techniques that are used in reinforcement learning. So let's come to the first network. This is called the class capture network, and it's a 3D unit architecture that takes in noise as input and gives us a class sample as the output. Then this class sample is shown to the victim, and the victim is asked to give us the label back, and this label is then one-hot encoded. So in the next slide, I'll show you a graphic of the model on how this class capture network works. So we are passing a Gaussian noise to the class capture network that is of the shape FHWC, that's frame, height, width, and channel. This generates a class sample which is passed to the victim, which gives us a vector called L1, which is the one-hot encoded class label. Now, I want to emphasize the fact that these class labels are orthogonal. If it says, the victim says that this sample is of class 1, then it will be of the form 1000. And if it says it's of class 2, then this L1 vector will be of the shape 0100. So we want to emphasize the fact that for same classes, the dot product of L1 will be 1, and for different classes, it will be 0, which is something that happens practically when we are doing a black box attack. So what the things that I just explained to you right now have been written into this slide. So coming to the second part of our network, which is the most important, the most salient, and the most novel feature of our network, is that this L1 vector, which is the one-hot encoded class representation that we obtained from the victim, is shown to another network, an autoencoder network, to generate another vector, L2. And this autoencoder is only intended to capture the class correlations, which we are doing by exploiting a very special property of autoencoders, which I'll elaborate later. So this, as you know, in autoencoder, our input and output dimensions are always same. So the obtained L2 vector is of the same shape as L1 vector. So you might be asking, what is the advantage of adding this second network to the mix? So this second network's only task is to resolve the issue of orthogonality that comes from the labels. So once we resolve this issue of orthogonality, we can use conventional classification losses like cross entropy, focal losses, etc., which can open a lot of diverse approaches down the line, where we can use even more learnings that are happening in the conventional classification architectures to exploit into our black box attack model. So this is a graphic of how the correlation capture network works. You can see we are passing the L1 that we obtained from the victim after generating a class sample to the correlation capture network, which gives us back L2. And the L2 is captioned as class label with added synthetic correlations. Now, very important question that is left to address is how are we getting this synthetic correlations? So as I mentioned, we are intending to exploit a very unique property of autoencoders to obtain these synthetic correlations. This property is that autoencoder networks inherently have a memory built into them. Say we have a batch of 1000 class samples that we obtain from 1000 noises. So once we show these to the autoencoder will see that, say, I got 800 images, 800 L1s as of class 1. Then I got some from class 2, 40 from class 3, and so on. So inherently, it will learn the ratio that is being reflected by this. Inherently, it will learn a ratio of the classes that is coming out from the victim, which will reflect that how similar classes are getting activated within the victim. So we plan to exploit the fact that autoencoders have a memory built into them. They have an inherent memory into them to capture these synthetic class correlations. So effectively, what we have done over here is without using any logic, without using any data, without using any known class correlations, we have both generated a sample of that class, and we have also somehow managed to capture its correlation with the other classes too. Right? So coming to a bit of a formal mathematics behind our solution, the two logits L1, L2, L1 that was obtained from the class capture network and L2 that was obtained from the correlation capture network are combined as L1 plus lambda L2, where we determined lambda to be experimentally quite small. In our case, we chose it to be 0.01. So to back this experimental conclusion with our intuition, what we felt is that the model, why this value works, is that a major emphasis is still on the class label. So we want the class label to be the dominant factor when we are generating the final embedding before passing it to the cross entropy loss. So by using a smaller lambda, we are effectively muting the contribution done by the correlation capture network. And practically also this seems very feasible, because if you see in any practical CNN how logits appear before the final classification layer, say my CNN wants to say that this sample belongs to class 0. So practically what we observe is that the output logits looks something like 0.9, 0.1, 0.01 and so on. So the major class that is the CNN is predicting is quite high when we compare it to the other classes. So once we obtain these two things, the loss is individually backpropagated through the network separately, which enables them to learn independently. We want to emphasize that the fact that we have isolated the two tasks between the network, and we want to focus on the independence so that each network can focus on its own task. By doing all this, we get a network, the class capture network, that will generate a sample for a single class. So we will get this one class capture network. So this happens for one particular class. Similarly, we repeat this exercise to generate these class capture networks. Say we have 400 samples in a data set, 400 classes in a data set. So we make 400 class capture networks. Now, the most important question that is, I think, left in everyone's mind is, why do we title our approach overfitting is all you need? The fact that we only need to generate some n number of fixed samples of a class for a black box approach to work, or for say a gray box approach to work, enables us to exploit the fact that we can overfit this class capture network over here. So how do we achieve this overfitting? Say I want only 1000 class samples to train my target student network. So what I'll do is, this Gaussian noises that I'm passing to the class capture network, these will always be seeded. So I'll always pass some specific 1000 seeded Gaussian noises, and I want my class capture network to overfit on these noises. because my goal is not to generate 1 million samples of a particular class or generate n million samples of a particular class. My goal is to generate 1,000 samples of this particular class, which the victim always says belongs to a particular class. So we want to exploit this fact, and that is why we want our class capture network to always overfit on this Gaussian noises, which we are enabling from the fact that we always seed our Gaussian noises, and these seeds are fixed over the epochs. Right. So that's it from my end. Now my friend will take over and describe you the conclusion and the result.
So we were, yeah. So we could provide the proof of concept for a small fraction of the data that we figured out 10 classes. Then, since due to limitation of the infrastructures, we trained our model extractor for 10 epochs and generated the all classes. And here are the results which we obtained for our action classification on Swinty model. We achieved 0.25 accuracy, and for video classification attacks on both black box and gray box, we achieved 0.16 accuracy. This is because our approach was very general. At both gray box and black box settings, the scoring is similar. So that's presentation from team 3. Thank you.
Team, thanks for the presentation. Amit, you want to ask that black box, gray box question?
Yeah. I just had one just a question. So across both problems, both attack strategies are yielding same results, exact same results. Right? Does that hint you to something can you explain why?
Let me paraphrase the question. How do you interpret that a black box for both the P1 and P2 is giving you exact 0.6 and the gray box is also giving exact 0.25? How is that?
So actually our approach hinged on the fact that we were planning to so our approach is on the fact that we are planning to exploit the data generated from this black box attack into the gray box while supplementing it with the data set that the 5% data set that we were sampling. But due to infrastructure constraints, we were not able to get adequate amount of processing power and GPUs due to some constraints. We were not able to completely generate all the data. So we did a POC over 10 classes.
Okay. So the result that you have submitted is only for the POC for the 10 classes.
Yes, sir.
Okay. Then the next question is that for the gray box, if you utilize that 5% of the data, which is already at your disposal, plus whatever that you have generated for the black box, then your gray box accuracy should be much higher, right? Even for this 10 class proof of concept.
Yes, of course, it should be higher, but we thought having a good black box model would be essential for training the gray box. Actually, we tried to overfit this gray box model, a small model, but it doesn't work very well. It doesn't generalize to other classes. If we have the 11th classes or if we train for a smaller data set, then we thought let's focus on the black box setting first of all, generate more data and then train. So we are positive about the fact that if we train on the given 5% data, it will improve. But right now we provided the result for only the black box data that we had.
Understood. Can you please go back to your slides where you have this class capture network, please? Yes.
Yeah, I'm trying to understand what the class capture network could look like. So you are forcing the victim to output a specific class, right?
Yeah, the class label, right?
Right. That means you train this once for one class output only.
Yeah.
So there is a separate class capture network for every class. That means for a data set with 600 classes, you would have class capture network 600 times, trained differently. Am I right?
Yeah.
Okay. One. Second, you are forcing the input dimension to be FHWC just because you want the class sample dimension to be FHWC. And there, without looking at the internals, it could be a fully connected network, or have you used anything special there inside class capture network?
We are using the fully connected network, so that's a fully convolutional network, a variation of UNet to work in a 3D space.
UNet in 3D.
Okay.
Yeah.
Okay.
Okay. And
skip connection.
Yeah, how do you know that the autoencoder that is working on L1? How do you measure the performance of this autoencoder? Do you fix again based on the same logic? Can I imagine that in this architecture you just insert the autoencoder?
So
the question is for the next slide where you have the L1 is there and you use the autoencoder to generate L2.
Yeah, right. So first we try to run this network in a naked manner without attaching this autoencoder after the network, using techniques like Gumbel softmax or manually like adding some noise to the generated L1 to make sure that it works with cross entropy. But then we realized then we tried out this approach using this autoencoder, and we saw that the dropping of cross entropy loss while training was quite fast. And the model tended to converge a little faster, and the performance of the cross entropy was better. So that is why we proceeded ahead with this autoencoder.
Okay, but autoencoder's main job is to condense the probability distribution function. And here, if for your 10 classes, which is coming as an input, what was your autoencoder giving you output?
Sorry, can you repeat? I did not get it.
Okay. So autoencoder generally has, first of all, have you used the fixed autoencoder or the variable autoencoder before I ask my question?
Fixed autoencoder.
Fixed autoencoder. So 10 input, 10 output, right?
Yeah.
Yes. What is the benefit of this here, the fixed autoencoder?
Like we want to have the same dimension in the input and output, since like we experimented with different number of nodes in the input side and output side, but we found out that while we were back propagating for the fixed autoencoder, the results were like better. So since it may be due to that, the fact that the one hot encoding are added some noise in autoencoder and they are more generalized or regularized.
Understood. So now tell me that autoencoder, when it was in the first phase, when it was reducing, what is the lowest number of neurons that you have reached?
So 128 neurons. So the input dimension is 1,400 for the kinetics 400 data set, and then it dropped down to 128.
Okay. So the 400 classes probability you have dropped down to 128 things, and then you can regenerate it.
Yeah.
But I'm just now wrapping my head around. You said that you have done the POC for 10 classes only. So it should be 10, 1 cross 10 and 1 cross 10 as the input and output, right?
So while we were training, what was happening is that we only trained this class capture network 10 times. So effectively, like the dimensions of the network were intended to work with 400, but we only trained this class capture network 10 times. So we have only got the result for that 10 specific classes that we trained for.
Okay. But then you are assuming then with this autoencoder is that this 400 classes share some kind of properties, right? And then if you go back to your previous approach, you say that the classes are orthogonal. How does these two things go together?
So what happens is that in the
Hello? We lost the audio.
Vivek Mittal, are you Prajwal?
hello, am I audible?
Yeah, Vivek, you're audible. Can you check what happened to Prajwal?
Yeah, I'm Prajwal. Like we are sitting next to each other, so I'm.
Yeah. Okay.
So. Okay. So as I was saying, say once we get to a significantly trained stage in the class capture network, we pass 1000 images in an epoch. So what will happen is that, say our victim says 900 images from class 1, 2 images from class 2, 3 images from class 3, 40 images from class 4, and so on. So our intuition is that this autoencoder will learn the ratio of these images, and then it will try to generate those synthetic correlations.
Understood.
Okay, let me put it again. The class capture networks are independent and separate networks for each class, whereas the autoencoder takes in all the classes as input and then tries to find the correlation between samples of a specific class. Am I right?
Yeah, exactly.
Okay.
We have to exploit the fact that similar looking classes will activate the similar neurons in the victim model. So that is something that we are trying to exploit with this autoencoder.
Understood.
Got it. Okay.
Thanks.
Thank you very much.
Good luck to you.
Thank you.
Thank you, Team 3. Prajwal, you can stop sharing your screen. And Team Team 14, can you raise your hands so I can make you presenters? Yeah, Team 14, now you can share your screen and just tell when you're ready.
Is my screen visible? And
Yes,
am I
it's
audible?
yes, your screen is just your screen is blank right now. Yeah, it's now visible. Yeah, it's visible.
Okay.
And you're audible too.
Thank you. I guess we can start, Niyati.
Yeah. Good afternoon, everyone. We are Team 14. From self-driving cars to vaccine synthesis, AI-based algorithms are ubiquitous in virtually every scientific domain by virtue of the immense potential and promise they hold as a technology. However, the cost of success comes at the expense of safety, as the growing dependence on data-based and data-driven solutions makes us increasingly vulnerable to attacks that can result in catastrophic damage of reputational, financial, and intellectual property. Thus, the need to defend against such attacks motivates the study of performing successful attack strategies in the first place. So, in accordance with the problem statement, which is already explained by my previous team members, our flow of presentation would be: first, we brief you with a background of our strategy, followed by implementation, and subsequently our analysis and results obtained. So, to begin with, the problem statement was a tough nut to crack, given the Kinetic 600 dataset is 5 times larger than BDD 100K. Besides, the classes are very closely related. For instance, can you spot the difference between the classes kicking soccer ball and kicking field goal? Inching closer to reality, we've supposed to extract the model in a black box setting, that is without knowledge of the dataset, and in gray box setting, which is just 5% of the original kinetics dataset. So, to ideate and build upon our strategy, we conducted a thorough literature survey of some relevant research papers. There are 3 foundational papers that motivated our solution to the problem statement. We are aware that knowledge distillation is a well-known method to transfer or compress a large teacher model into a small student model. This is done by inferring the teacher model with the input data and its output is used as labels to train the student model. In the first paper, robust knowledge distillation, we use an adversarial generator to output images that maximizes the disagreement between teacher and student, which enables the distillation process to be much more quicker. In the second paper, Maze, we are trying to distill the model, but without data. Hence, the generator is trained using disagreement between models. Another contribution of this paper is that the gradients are computed using zero-order gradient estimation, which facilitates black box access of the teacher. So, in addition to these 2 papers, another paper is data-free model extraction. The work utilizes forward difference method for zeroth order gradient estimation, which is basically perturbing the input space to get output samples to average the gradients. It also introduces that when we have access to logits, L1 loss has proven to be better than KL divergence, as it prevents vanishing gradients and provides faster convergence. However, in our given problem setting, we do not have access to logits, leaving us with KL divergence as the only alternative. So, our model extraction has been inspired by the above mentioned paper, proposing a data-free model extraction approach for static images. Subsequently, we extrapolate the strategy to video-based models, taking into account space and time tokens of videos. Thus, we aim to minimize the number of queries made to model to be extracted and at the same time maximize the student model's accuracy. Now let's move forward to understand the approach.
Arriving at the solution to the problem statement, we developed the showcased end-to-end framework of our extraction strategy. Here we have a query generator which generates random video samples which are then passed through the student and the victim model. And since we only have access to the predicted labels from the victim model, we chose to use the KL loss and we backpropagate through the generator model using zeroth order approximation of the gradients. Now looking into each of these in more depth, we first have the generator. Our generator serves as an adversary to maximize the disagreement between the student and the victim model. The generator we took in our implementation is the temporal GAN, also known as TGAN. The generator of TGAN consists of two subnetworks, the temporal generator and the image generator. A latent vector is passed through the temporal GAN, which generates 16 latent vectors with some correlation, and each of them is then passed through the image generator, which generates 16 frames for a single query video. Now, as already discussed, the victim model with regards to PS1 is Swinty, and for the PS2 is MovieNet A2 base. Now, since it's placed in a black box setting, we do not have access to the weights or the gradients for backpropagation, and we only have access to the predicted labels from the victim. Coming to the student model, after a lot of consideration, we have chosen the video vision transformer, also known as the VVT. The student model here serves as an adversary to minimize the disagreement between the student and the victim model. The VVT model is based on factorized encoder and is computed on a sequence of spatiotemporal tokens that we extracted from the input video. The student model, along with the victim model, performs inference on generated queries to compute the loss function, which uses KL divergence. Next. In this slide, we will be highlighting our approach, which we effectively implemented in the black box setting and subsequently altered for the gray box setting. Now for the black box setting, we do not have access to any kind of data. So we trained our query generator using only the disagreement between the student and the victim model. This combination of student and the victim model is used as a discriminator to train a query generator model. However, for the gray box setting, we were given an exemption to use external dataset and the 5% of kinetics dataset. Thus, we modified our query generator. We used the actual 5% of kinetics dataset along with the temporal GAN pre-trained on UCF11 dataset to generate the queries. To prevent our model from overfitting on the 5% of the dataset, we introduce a threshold parameter. This threshold parameter decides the percentage of real and the generated data in a batch. We chose UCF11 dataset as it has similar classes to our original dataset, and the queries generated will make our model more robust to validation and testing. This parameter significantly improved the accuracy of the student model, which we will be covering in the analysis section. The modified query generator generates more quality queries, thus reducing the number of queries needed to extract the target model. Moving on to the implementations part. Since the student model is trained against the labels that the teacher model predicts on the query video, so from moving from images queries to video queries, we customized the zeroth order estimator to work with an additional axis that represents the temporal characteristics of the sampled video. For the hardware part, we use 3 NVIDIA GPUs and an Intel i9 CPU with 16 cores to run and train our models. Moreover, our implementation was entirely done in PyTorch Lightning to extensively parallelize our compute pipeline. So this is all for the implementations details. Now let's move on to the analysis part.
Yeah. So into the analyzing our approach, we would like to analyze sub-modules of our whole pipeline. starting out with the generator. So before understanding how our generator fared, we should understand what the true data is or the true data distribution is. That is the kinetic 600 data set that you can see to the right of the slide. As you can see, multiple classes there. We also have a generator that is pre-trained on the UCF 101 dataset that we explained earlier, where you can see outputs not having very distinctive classes, but has good amount of distribution to the original dataset. This was used for the gray box setting, as we explained, in calculation with the kinetics dataset, using these both for training. But as you can see to the left of our slide, where we have the output from the generator of the black box, it is not interpretable. It is very difficult to understand what is going on. But this is able to distill the teacher to the student model, just because we have trained it to increase the disagreement between the teacher and the student model, and not focused on the visual fidelity of it. So keeping this in mind, moving forward to how we had the exploitation or exploration criteria, what exactly we mean by the exploitation is training on the kinetic 600 data set, that is the 5% of the 600 data set. This is exploiting because we are going to get a higher score on the training data, but this would make us lose out on the best solution or the optimal policy or optimal model that by exploitation, we mean using the UCF generator for generating more samples that are not seen previously. And as increasing the random input, we get newer and newer samples, increasing or diversifying our input space. So using the best of both worlds, we have tried to sample out a few from the 5% of the dataset and the actual generator model that is using the threshold value that we explained in the previous slide, earlier slide. Basically, here the threshold explains the percentage of how much random sampling is happening from the real data set and from the generator model itself. As you can see on the table, we can see an increase in the validation accuracy as we decrease the threshold. That is, when we balance out both the data sets, we get a better validation data set while taking a small hit on the training accuracy. This helps us overcome overfitting very easily, as it is clearly seen here. Then moving towards the plots on how they fared. Basically, in the gray box setting, we got good amount of convergence for both the problem statements. As you can see, the SWIN-T and the VVT model that we trained here got a very good convergence, and a similar result is seen for the MovieNet. But for black box setting, with the limited number of trial runs that we had, we saw little success with a little amount of convergence. And with the limited amount of time we had, we got this far. So before going forward to actually going to the tabular results, I would like to address a few open-ended limitations that we had for our approach or the problem statement itself. That is, black box for video are very expensive. They are expensive because when you have a generator for a video, the random noise that the video starts out with makes a huge or vast search space for it to converge. So one, it makes the generator very uninterpretable, as we explained in the generator analysis. So it made us also difficult to analyze what the progress of training was. So with this, we also had a similar black box approach for an image dataset, that is CIFAR 10, which is a very simple dataset with 10 classes. It required nearly 20 million queries to get accuracy up to of 92%. But our problem statement has nearly 400 or 600 closely related classes, also being videos, that is having 16 frames. So this makes our problem statement for the black box setting way more challenging than anything out there. The other limitation that we would like to put forward is the access to compute resources. Because of the limited compute resources, we put a justificable amount of training for each model or each scenario, that is 400 epochs, which took around 70 hours to run parallelly on 3 GPUs. So with these consistent training scores, we have this tabulated data. So this 400 epochs rounded off to 1 million queries approximately for all the scenarios, just changing due to batch size or few parameters. But as you can see, with this limited amount of training, we could get a very good validation accuracy for the gray box. This is top 1% accuracy for gray box, that is around 57%. But for the black box, we get 4% of validation accuracy. This is again because of the limitation addressed before. The other problem statement that we had was for MovieNet base. This results are 14 and 1% respectively for the gray box and the black box. The results are not similar just because of the limited amount of trials or experiments that we could run for it. there may be bugs, or they may be also due to the reason that we didn't parameter tune them.
So on that note, we would like to conclude. We are extremely grateful to BOSCH to have provided us with an interesting problem statement. We witnessed our steep growth in the past month. Although the development of the problem-specific attacks would have ensured a reasonable solution to the given task, we invested a significant time and efforts in ensuring the generality of our solution, and thereby solved the primary objective of this event, to address the challenge of securing AI models in general, which in turn requires exploit a set of models. Thanks a lot for your time. Now we are open to questions. That was a 15-minute.
Thank you, team, for the presentation, and really liked some of the approaches that you have done. On the result, if you go to previous slide on the results, I have a few questions there. Could you please go to the previous slide, please? Yes, here. Can you help me understand that why the performance, especially on the gray box, for the SWIN-T, you have 57.57 with 0.72 million accuracies vis-a-vis on a gray box. With even little higher query than 0.72, you have much lower validation accuracy. Because you said that you invested significantly in generalization, I would have expected the gray box results to remain at least comparable. Do you have an explanation for this behavior in the result?
It was mainly because while training the MovieNet, we were aware of a few bugs, maybe that being the input space of the MovieNet and SWIN-T being different. That is, MovieNet takes 0 to 1, while SWIN-T takes -1 to 1. But we use the same code to train it. So with the limit, while we got that result was very bad. So we ran a few last-minute tests to get the MovieNet accuracy, but we didn't have 3 days, 70 hours basically, to train it for all the epochs. So the result you are able to see for 14%, that is with the wrong input. So that is between -1 to 1, but MovieNet doesn't accept that. So that was a bit of a problem. But yeah, to how much ever we tested the gray box for SWIN-T, in n number of tries, we got a similar validation accuracy. So we believe with the given amount of time, if we had a bit more amount of time, we could get a similar result for MovieNet, as it's not very difficult compared to SWIN-T.
Okay. Thank you for that explanation. So after you submitted this, and when you realized that this is a mistake in the input?
Yeah, no, it was before submitting. It was just a day before submitting. So we still didn't have 70 hours of time to train it, put it for training for all the 1 million queries. So that was when we just compromised and put the results that we got when the input was -1 to 1, and that was 14%, because that was not the input space for MovieNet.
Understood. So my question is that happened on 22nd, and now today we are sitting and doing it, let's say 26 4 days. Did you give a run for a retraining after correcting your inputs?
We did not, because we are not allowed to change any values from the day that we submit. So
that I understand. I just wanted to know that to what you are saying to back up your claim today. Do you have a number that how it will be?
No, we don't have, but we could surely try that out.
Okay, fine. Yuvraj?
First of all, I like the way you have looked into the data to understand the complexity of the problem. That's a very good starting step. Do you have a justification why Vivid was chosen model? Hello?
Yeah, I guess VVNet was one of the very baselines, or one of the most famous approaches for video classification in the domain that we were trying out. That is, it had good accuracy for both Kinetics 400 and 600. So we decided to choose it, and it would be ideal. But our main focus was not on the student model exactly, because we could put any other model, it would get the similar result for us. So they are modular, and we can change it to anything else. No specific reason to choose it.
Okay. And your focus, at least so far, was completely on the temporal gun improvisation, is it? Or where did you have most of your focus on?
Sorry, our focus was on. Could you
repeat? Did you try improving the generator or the student model in the whole the data-free model approach?
So in the data-free model approach, we used a completely different kind of GAN. So it is temporal GAN, which has another dimension itself, and the way it works is different. So there was not much to change for the GAN itself. Because at the end of the day, this is just the image generator. So we didn't see a much use to change it. And because we mainly focus on gray box, as you can see from the results, gray box, we use a pre-trained network for the same temporal GAN, that is with the UCF. So we didn't exactly think of any losses or any kind of methods to exactly improve the GAN. But yeah, our main focus was to improve the student model's accuracy for both validation and test train. Because that was the problem we were facing for when we were training the gray box, because 5% overfits the model and the validation score goes down, as you could see. So our main focus was mainly there. But yeah, we didn't have any specific loss or any specific constraint for the GAN.
All right, thank you. We have no more questions. Thank you.
Thank you. Thank you, judges.
Thank you.
Yeah, Somnath, you can stop sharing your presentation. Thank you, Team 14. Team 16, can you raise your hand so I could add you in the presenters? Team 16, I see only Soumya Agarwal from your team. Is that it for the presentation? Okay, I see Chaitanya. Yeah. Okay, Team 16, there are 3 people from your team. Is that them for the presentation? Can someone unmute and confirm? Can you repeat it, Aman?
2 more students are just joining. Can you please wait for just a few seconds?
Yeah, it's fine. Yeah.
Aman, could you please tell Piyush Pandey to join again? He was removed from the meeting.
Yeah, I have informed him. He has joined.
Yeah, Team 16, you can start presenting now and just tell me when you're ready. Team 16, you can start your presentation now.
If you are just presenting the screen, please wait for just a minute.
Yeah, it's
Sanjay?
Yes, sir.
Are we waiting for the team to start?
Yes, sir. We are waiting for the team. Team 16, are you able to present your screen? Yeah, we can see this.
Soumya, if you're speaking something, you're not audible.
Hello, am I audible now? Hello.
Soumya, yeah, you're audible. Yeah, you're audible.
Okay, thank you.
There's
ma'am.
a lot of background noise. Can you just,
Oh, just a second.
you can continue.
Hello.
Soumya, you're audible.
Yeah.
You can continue.
Yeah, so let's talk about a well-known autonomous vehicle manufacturer company, Lyft. They are known to be one of the best in creating artificial intelligence-based self-driving cars. They use highly scalable and computationally efficient machine learning algorithms. Now, what if someone gets access to their underlying computationally efficient algorithms? They can create a new company, leading to a considerable loss to the parent. Hence, to prevent this, the first step would be to check if the model is extractable or not. Hence the problem statement. So the problem statement requires us to extract video-based models across two tasks, action classification task and video classification task, in two settings, black box and gray box. Now, in the black box setting, we are not aware of the model's architecture and the data set it is trained on. So we train our model by passing generated data as a query to the victim model. In the gray box setting, also, we do not know about the model's architecture, but we do know about the dataset that the victim model is trained on. The attacker has the access to 5% of that dataset, and the use of other publicly available datasets is also permitted. Now, let me elaborate on our work for the action classification task, in which the model to be extracted is SWIN-T, which is trained on Kinetics 400 dataset. Now, dataset insights of the black box setting. Since we could not use any already existing dataset, we generated the data by passing noise to the generator and passed the generated videos as queries directly to the victim model and a student model. Next is dataset insights of the gray box setting. As we could use any publicly available dataset, we chose something v2 to pre-train our attacker model. It is also an action classification dataset which has 2.2 lakh videos distributed across 175 classes that show humans performing basic actions like moving something down, pushing something right, which is why it is called something dataset. Along with it, we also had the liberty to use 5% of the Kinetics 400 dataset. Now, nextly, talking about the intuition behind the choice of model for black box setting. We needed a model that is expected to be easier to train and easier to train with a generator network. Nextly, it should be lightweight, ResNet based, so that the training is fast and smooth. Lastly, it should be able to achieve a decent accuracy close to the model to be extracted. The slow fast model qualifies all our requirements and achieved 78.8% validation accuracy on Kinetics 600 dataset and 75.6% on Kinetics 400 dataset, as you can see in the image. Nextly, talking about the model intuition for gray box setting, we chose temporal difference networks TDN because of some considerable reasons. Firstly, it has a ResNet backbone which is easier to understand and computationally less expensive. Secondly, it was working well on our dataset, that is something v2 dataset, and had achieved state-of-the-art performance on it. Lastly, it was proposed very recently and had a new architecture, so it was believed to give better results. Nextly, another area of concern was to use the best 5% data out of the whole Kinetics 400 dataset. For this, we had two options. First is to pick out the samples with highest deviation from ground truth, and second is to pick samples, random samples, evenly distributed from all the classes. In the first strategy, there are high chances that we pick outliers. So we chose the second strategy, that is random sampling of the data evenly from all the classes. Nextly, let's move forward to the action classification task in which the model to be extracted is MovieNet A2, which is trained on Kinetics 600 dataset. Now, everything is similar. The dataset insight is similar in both the cases. Just the difference is in using Kinetics 600 dataset. And for the gray box setting, we had to use 5% of the Kinetics 600 dataset. Please change the slide. Yeah. So the training pipeline of the black box model. Because no dataset was given to us, we needed to give synthetic inputs to the models. To generate those synthetic data points, we took help of a generator, which would take random noise as input and generate a vector, which would represent a video. This video would be fed to both the student model and the victim model. The outputs of both the models goes through the L1 loss. The ultimate goal of our student model is to try and mimic the behavior of the victim model. We try to achieve this goal by making the generator create such outputs that would get the student and victim model output different labels. In short, the generator is trying to make learning difficult for the student while the student is trying its best to copy the victim behavior. Now let's talk about the training pipeline for gray box setting. What we did differently here was to use a dataset called something v2 for pre-training the student model first. And then instead of using a generator, we brought in the 5% Kinetics dataset that we had in order to extract weights from the victim model. Nextly, the black box setting extracted model. Slow fast model is used for video recognition in and it involves two pathways. First is the slow pathway, operating at a low frame rate to capture spatial semantics. And second is a fast pathway, operating at a high frame rate to capture motion at fine temporal resolution. Next, for the baseline network, we use DVD GAN and achieve state-of-the-art. DVD GAN is a generative adversarial network for video generation built upon big GAN architecture. It uses two discriminators, spatial and temporal, where spatial discriminator critiques single frame content and structure by random sampling K full resolution frames and judging them individually. Temporal discriminator provide Gaussian latent noise with the learning signal to generate movement. Next, baseline network architecture for TDN. So TDN generalizes the idea of RGB difference to devise an efficient temporal difference module, TDM. To fully capture temporal information over the entire video, TDN is established with a two-level difference modeling paradigm. For the local motion modeling, temporal difference over consecutive frames is used to supply 2D CNNs with finer motion pattern, while for the global motion modeling, temporal difference across segments is incorporated to capture long-range structure for motion feature excitation. Nextly, let's talk about the challenges that we faced. So first is, due to unavailability of resources, our training was relatively slow and we were unable to use models with higher complexity, which might have led to better performance. Secondly, during model extraction in black box setting, we noticed that the generator model was stronger than the student model. We think this was because the task of generator was too easy for the generator model to mislead the student. Since our student model was dumb initially, who would misclassify any video given. To tackle this problem, we first pre-trained the student with random data. As soon as we saw that the loss further stopped decreasing, we put it back together with the generator to make it more robust. Thirdly, we were limited to use very low batch sizes because which leads to poor generalization. We tried to overcome this by applying gradient accumulation in the training pipeline. Now let's talk about the tech stacks used. We use PyTorch, video augmentations, NumPy, Pandas, Matplotlib, and Google Colab. Nextly, the further improvements and future scopes. So first was that we can experiment with different student generator architecture. Secondly, we can try different training strategies like gradient accumulation, gradient estimation, etc. And third is the trade-off between high fidelity and high accuracy in the gray box setting. Next, the references of the papers we used and the architectures we used. Thank you.
First of all, good job, especially the use of TDN. That is interesting that you have taken the image use case of data free models and added TDN on top of it. I only had a question on the choice of why and how you got from TDN to the DVD GAN model. Hello? Hello?
Is the question clear?
Team 16, I think you stopped presenting your screen, so if you could present your PPT, it would be nice. And also, I hope the question asked by the judges was clear. You can also start presenting your PPT. You stop sharing the screen.
I would like to answer. Actually, both the models in the question have two different jobs. The TDN network was used as a student model, but the DVD GAN was actually used as a generator model. The task of the student model was to get the weights extracted from the victim model, whereas the task of the generator was to try to make the learning of a student model difficult by making such samples or such output videos that would confuse the student model into outputting different labels than what the victim model is outputting.
but it is still not very clear to me. Did you go from DVD GAN to TDN network or the other way around?
Sir, actually, what we did was we did model extraction in the black box setting first. So we used DVD GAN first, and in the gray box setting, we tried to use the DVD GAN first, but we found out that using 5% kinetics data set directly instead of using the synthetic data set generated by the DVD GAN was better.
Okay.
What I mean is that using 5% data set was giving superior results as compared to using the DVD GAN. So we replaced it with the 5% data set in the pipeline.
Okay. All right. Thank you.
Thank you, sir.
Thank you, Dean. That's all from our side. Good luck.
Thank you so much.
Thank you.
All right. So with this, we come to an end of all the presentations that we had for the BOSCH HyPrep PS model extraction for video classification. We had a total of 12 presentations today. Team 9 couldn't present, unfortunately, due to certain unavoidable circumstances. So teams, I hope it was a good experience.
Maybe they are directly.
Yeah, Srinji, what about the team 18?
Yeah, so team 18, sir, they had not submitted their second score, their documentation, their code, as well as the final PPT. So they had submitted only the first score. And I even tried reaching out to their members, but they did not respond. So I am assuming they do not want to continue in the competition. Like if you want on the score sheet, you can still like mention their first score submission scores. But I mean,
Yes, we will do that. Yeah, so we will do that based upon whomsoever has submitted the first one. There will be a score for that. Whomsoever has submitted in the phase 2 score will be there, and teams who have presented today the scores will be there.
Yeah. Okay, so participants, I hope it was a good experience for all of you, and I hope you presented well. And
Srinjay, one more point. If it makes sense, and if the participants are there, whomsoever wants to give us any feedback directly also, we would like to hear from them for the next 5 minutes. So,
like how was the challenge overall?
Challenge overall and other things. So whomsoever wants to raise their hand, they can. And Rohan is here. He has raised his hand from the team 2. So please.
yeah, he raised his hand, but then he lowered it again. Okay. So if anybody wants to say anything, give any feedback to the panelists, you can raise your hand. I will give you presenters.
Hello, can you hear me?
Yes, Rohan, we can hear you.
Yeah, so two things actually. One was, I think we faced some network issues, right, in the starting.
Correct.
So I think the doubt session was cut short for us as well. So if you would like to ask something and continue that, I think Srinjay allowed us to do that. And the second thing is, I see a lot of teams have actually used these action data sets, that the video classification data sets, similar to kinetics, and they've like used pre-trained models and things like that. But I think it wasn't allowed in the initial doubt session. You guys disallowed it. So like, what is the policy behind that?
Sure. So Rohan, first to answer your first questions, yes, you had a network connection, but one of your teammates picked up the questions and given an answer and helped clarify the doubt. So we are no longer in the need of any further clarifications. So thank you for offering that. On the second one, the teams whomsoever has used it, as far as what we know, we are also looking into all of the objections which are raised. Also, Srinjay informed us that there are certain objections which are raised, and we are taking due note of those particular things. So I will not be discussing policy openly. We had told what are the rules, And wherever we see the rules violations, we will take appropriate measures.
Okay, great. Thanks.
Hello, am I audible?
Yes, Iman.
So like my only feedback is regarding the doubt session we had with you, sir. So what I feel is that that doubt session was very like confusing. Like I don't know what to say, what word to actually say, but uh, there were many instances where we feel that for the same question you answered one thing, and when the same question was asked in another phrases, you can say you answered differently. So maybe what could have possibly done is that standard FAQ could have been launched like after the video session. FAQ document could have been launched so that in case is there any discrepancy sorry discrepancy क्या कह रहा हूँ मैं कोई if there was any problem
हिमा हिंदी में बोल दो जो बोलना है
नहीं देखो कोई भी डिस्क्रिपेंसी होती तो वो सॉल्व हो जाती मेनली बस इट वाज मेनली दिस इशू कि फॉर द सेम क्वेश्चन या
ओके अंडरस्टूड सो आपने जो बोला कि सेम क्वेश्चन के लिए डिफरेंट डिफरेंट आंसर्स दिए वो इसलिए दिए गए थे कि आपके कलीग्स सेम क्वेश्चंस को डिफरेंट डिफरेंट तरीके से पूछ रहे थे और उनको वो डिफरेंट डिफरेंट आंसर्स चाहिए थे इसके लिए ही हमने उसके बाद श्रीजय ने आपको एक चीज फॉरवर्ड की होगी कि आप पहले सबमिशन के बाद हमने क्लियरली बोला था कि लिटरेचर में बहुत डिफरेंसेस हैं what is the meaning of white box, what is the meaning of black box, what is the meaning of gray box, and the major confusion comes in the gray box, and that's why we made it extremely clear that what we mean by the black box and gray box. However, that is what happened, that everybody interpreted in their own way despite of giving 3 clear lines.
Okay. मतलब यही कि if we can have FAQ after the session, because many a time we would have to look at the recording again. On the other hand, if we had a document where we had this was the question asked, this was the answer. So that is my only feedback.
Sure.
We can have an FAQ after a doubt session.
Sure. I think we'll keep it in mind for next versions of this. Glad you voiced it out. Thanks.
So next time onwards, we will write in the problem statement along with the FAQs.
Yeah.
Great. Thanks.
Hello, am I audible?
Yes, Sahil.
Yeah, so like in the recording session, in the recording, you told like in black box, we can't use anything and not any images, not any pre-trained models. Only we can generate synthetic data. So like many teams have like done it. So like there must be a penalty like that you will do for this.
Sahil, I already answered that question. I'll again answer it. And this is what also happened in FAQ. We told exactly what we want. We have set the rules. If there are different interpretations, then the appropriate measures will be taken. However, what you consider as a white box, what you consider as a black box, or what you consider as a gray box is not the ground for the penalty. So I want to make it absolutely clear. Yes, according to us, and whatever we have said, we will put it in the letter and spirit.
Just want to clarify what you have said. For black box, nothing can be used, no pre-trained, nothing else. So for gray box, we can use any dataset except kinetic 5% of except the other 95% of kinetic.
Yes. And I think the black box, nothing can be used. That is not the case. If you use nothing, then you get nothing out of it. So for the black box, what we have said is that you cannot use any of the relevant information of the model or the data. Just to make it absolutely clear. And if you use a pre-trained model which is on the relevant data set, then again that is not considered as in a black box. This is also I categorically told in the same meeting.
Okay.
Yeah. Okay.
I would like to add, although there is this definition of black box, gray box being there, I think there are also other parameters that we will have to look into: the approach, the kind of models that is used, and how you systematically took from step by step, and how you differentiated, irrespective of what the definition was, how you differentiated a gray box from a black box. So there are those aspects as well that are being covered. So if that helps.
So penalty is only there on the results as such, to make it clear.
Okay.
Good. Anyone else who would like to give a feedback?
Excuse. Will we have these PDFs or the documentations or whatever shared with us, or like where do we find it if you want to like study it again?
That's probably a question to Stranger.
Yeah.
I think.
It's too
Okay.
strict. So will we be getting it?
Sorry, I missed your question. Could you once repeat it?
Yeah, so just for reviewing sake and curiosity, will we get the works of everybody? Like, will you open it to us or no?
I'm not sure exactly about this, Sahil. I mean, we wouldn't have any issue in releasing the presentations of everybody once the competition is over. So, I mean, once we get this score sheet from the company and we release the results, we'll then surely release the presentations. That is no problem.
Great, thanks.
Good. I think then, if there are no more questions or feedback, thank you teams who participated, and thank you Srinjay. It was a great event for us. We learned a lot from the students, and we really like the energy, enthusiasm, and the diverse thought process. So thank you for, as a host, as a participants, you have put up a lot of effort, and we are really proud of what you guys have done. The brightest minds of India, that what you were able to do. It's not only that the results what matters, it's the approach, it's the learning that you have is tremendous, and it's also for us extremely important that we facilitate as an industry not only the the jobs but also the learning, and take help entire ecosystems to come up to the next level of a challenge. So thank you for making us believe that we can do it even better next time.
Thank you so much, sir. Thank you everybody for the coordination. Thank you, Parmar sir, Yuvraj sir, Amit sir, for sharing your time inside for this session. All right. With this, we can close the session. It ends the meeting. Thank you, judges.